All right, good morning. It's Mr. Burkhart, and we are going to take a look at 4B to start with, choosing systems. A ball falls from rest from a height h. Consider the ball to be the system. Draw a dotted circle around the system. Okay, they did that. See the dotted circle there. The dot right represents the ball. Draw a free body diagram showing and labeling the forces exerted on the ball. It looks like force of gravity. So far, so good. Draw relative lengths. Okay, that's just boilerplate. They always say that. And on the grid below, sketch a graph of the net external force on the ball versus height. What are the units of the area under the curve? So the force is always the force of gravity. It's a constant force. It's the mass times g, so that's not going to change. So that's why they drew a line. Notice that they drew that line under in the quadrant where it would give you a negative answer, and so that's interesting. So the units of this area must be the units of force times units of meters, which will give us joules. And the area must be equal to the work done on the system. Okay. And the work is done. So it looks like we're kind of going back. So while we're here, there's a quick quiz over here on the side. Why don't you pause your video and just get out a piece of paper and quickly sketch the graphs, position versus time, velocity versus time, acceleration versus time, net external force versus time, net external force versus height, and pause the video and then come back, and then I'll work through those. I think that might be interesting to review. Thank you. Okay, welcome back. Position versus time. So we throw a ball into the air, write the ball, just what it looks like. It would look like, I don't know if I can actually write on this. Assuming I could. You know what, I'm going to have to, probably the easiest way for me to write is to do this. All right, it gives me a little bit of room to write. So the ball goes up in the air, right? Woo, comes back. Well, we want to know just the journey up. So up. So what does a position look like? Well, it starts off where the position is changing kind of a lot, right? And then, but as it goes up, the position changes less and less over time. So I think a graph like that. And you may disagree, and you should let me know. The velocity versus time, I'm pretty confident about the velocity versus time. I think that the velocity starts off with a positive velocity, and then it goes to zero and it's at the top. So that's a velocity graph. Pretty good about that one. The acceleration graph also, I'm pretty confident with the acceleration graph. Oops. Let's save that for something else. The acceleration graph, oh my God, it would be down here, it would be negative 9.8, right? So that's the acceleration graph. Way down below. The net external force versus time. So the force is mg, and also it should also be probably negative, I guess, technically. All right, so the force versus time. It's always applying a negative mg force versus time, applying the same force all the time. And then the force versus height will look basically the same as the graph that they already provided. That's what I think. So if I got it wrong, you should let me know. All right. So now part D. Did I finish this? Yeah. Part D. Fill in the energy bar chart to describe the energy of the system from when the ball is dropped to just before it hits the ground. Use the lines below to explain your reasoning. So this is just the ball. It's the thing. So there's some mysterious force outside of the ball. We don't know what it is. It's a secret force. It's doing work on the ball, right? And it's putting that work into the ball, and that's external work being done. And then as the ball falls, so there's just all this external work was done, I guess, to raise the ball up. It's all And then when it falls and it's just about to hit the ground, all the energy is kinetic. The mechanical energy of the system increases as the ball falls. Work is done by the gravitational force to increase the kinetic energy of the ball. Right, because it started, I don't know. Just, I'm kind of confused about this still. This whole, it had positive work. It had work. It had external work to begin with. I don't know. Now the Earth is included. Now this graph makes sense. It has potential energy to start with, and then it has kinetic energy to end with. See, that makes complete sense to me for part F. The total mechanical energy stays the same as the ball falls, right? Because you're adding, sometimes it's all potential. At the bottom, it's all kinetic. In between, it's part this and part that, and remains the same. All right. How are we doing on time? I have no idea. I should have started a timer. Well, there's a lot of these, so I'm going to go ahead and do at least 2 of them on the same video. 4C energy graphs. A ball is released from a rest at a height h above the floor. Consider the system to be the ball in the earth. Air resistance can be ignored. Potential energy versus distance fallen. In the following axis, sketch graphs of UG versus distance fallen. Okay, so it had all the potential energy, and then the potential energy decreased as the distance increased. The kinetic energy increased as the distance increased. The total mechanical energy stayed constant. One was going into the other. So now versus time. So versus time, the potential energy is, so you can see that they're curvy lines, and that's because the acceleration, because it's got this negative acceleration, which is slowing it down. So just talking about the kinetic energy, why does the kinetic energy, oh, it's actually speeding up, right? Are we still dropping a ball? Yeah, right. So it speeds up. So the velocity speeds up, but the kinetic energy changes with the square of the velocity. So as the velocity increases, the kinetic energy increases by a square, and that's why we have a happy face. And the potential energy is decreasing proportional to the kinetic energy. So that's one reason why it has a frowny face. Also, the height, as the ball accelerates, the amount of displacement the ball has over a period of time gets bigger and bigger and bigger. So the amount of potential energy is not changing at an even rate. It's changing relative to the height. The height is exponentially changing and getting bigger and bigger for every time interval. And so at any point, you can pause the video and read the red words. Quick quiz. Cart is released from rest at the top of a smooth incline, and the Earth cart system has 6 joules of gravitational potential energy at the top of the incline. When the cart is rolled halfway down the incline, the cart's kinetic energy will be 3 joules. All right, we have this incline. Oh, man. They can put a man on the moon, but they can't make a PDF you can write on with your finger. All right, so at the top of the incline, we have 6 joules of energy. Halfway down the incline, so if we were at the bottom of the energy, we would have 6 joules of kinetic energy. Here, we have 3 joules of each. That's what I think. That could be different, right? I mean, basically, the potential energy is changing as the height changes. We're halfway down the height, halfway down the ramp. I would just say it's equal to 3, but you could, again, call me out in class in front of everybody if I'm wrong. When the ball is halfway to the ground, its kinetic energy has more than, less than, or exactly half. Oh, look, I got it right. It's half. And so there's a nice explanation in red words. You can read about it. I think I really just kind of talked about that. Yeah, they're saying a lot of words. When the ball is halfway through falling at its time, its kinetic energy is less than. So this is why it's different. So when the position is half, right, MGH is half. So half of its potential energy, half of its kinetic energy. But for time-wise, it's we're being accelerated, so it actually takes longer to get to the halfway point because it's moving slower to start with, right? It's at 0, then it's going a little bit, then it's going a little bit more, then it's going a little bit faster, then a little bit faster, then a little bit faster. So it takes more time. It actually has less speed at the halfway. So as it's picking up speed and going faster and faster, when we're halfway through the journey time-wise, we are less than half of the speed at the end of it, right? The velocity isn't half of what it's going to be when we're done. It's much less than that, and that's why the energy is less. Yeah, I'm getting pretty good at this. You too could be pretty good at it if you studied it for 25 years. All right, I think I'm just going to stop sharing there. Actually, we're not, we already did D, I think, last week. And we're on E. So let's go ahead and stop the video and make a new one. And we'll pick this up on EFG.